Hi, everybody. Let me turn this down a little bit. All of these songs are so good. Welcome back to Chem 163. This is the last lecture. I'm not going to get through all the content. Like, that's just not a thing that we can do. There's too much, and I'm the instructor that would rather go slowly and surely and not finish the race, I guess. I don't know where I was going with that analogy, but that's okay. So we're going to do what we can, and it's fine. Let's see here. Really, the only, like, important events that I can think of upcoming are there's an exam on Friday. The lab that you did is due last week. Oh, I guess I could have put that down at the bottom too, but, like, duh. Every lab has been due on Friday/Saturday, right? So, I mean, at this point, it's old hat. Next week there is a final exam, and there is a review session scheduled for Monday. I'm going to put all of that in an announcement because I feel like that's important enough to note. If you have questions for the review session, you can, we could do it one of two ways. Like, we could either do a live one here, or I could just be, like, available that day. And you can post any questions you want in the class Discord. That might actually be better. Because I know not everybody watches these when they go up, and so a review session with nobody here is kind of pointless, right? So we're going to leave that up to whatever people want to do. So we left off Monday. We were talking about the differential and integrated rate laws. So the differential rate laws are the rate laws that we'd been talking about all along, where it's like Ka to the x, and then if we integrate that versus dA dt, we get this, which is the integrated rate law. So for each order, so this is the first order page, you're going to have a differential rate law, K times A to the 1, and an integrated rate law, which is this one. There's going to be one more equation that we associate with order, and that's half-life. But half-life is actually a function of the integrated rate law, where I put in, like, okay, I have something, and then at the end I have half as much of that, and then I solve for t. So we're going to get to that when we see that in the slides, but half-life isn't really its own separate equation. Now, because the integrated rate laws model the equation y equals mx plus b, when you plot them in various ways, you get a line. And we saw this in the lab. We were talking about in the Crystal Violet lab how if you plot absorbance versus time, and absorbance is our substitute for concentration because they're roughly the same thing, you get kind of a curve and not a straight line. But if you do natural log versus time, you do get a straight line. Or at least that's what everybody else got. And then we're going to do another one for second order, and we'll show what that is in a second. All right. So I just have a bunch of examples that I'm not going to really do because I've already done them. Like this example, we made up a problem last lecture where I said, okay, well, after 100 seconds, how much do I have left? And I should get this number. And we did the calculation using the rate constant from the graph on the next page. We totally got that value, so we could show that it is first order. And so I've plotted all these numbers in Excel, and here's the graphs. And you'll notice that the R² value for this is super close to 1, so this is very good. All right. Let's see here. Don't care about these problems. We've already really done them. Let's do this problem. We'll do it together. All right, so this is cyclopropane on the left. Cyclopropane, what it will do is it will rearrange with itself to become a non-cyclo compound. In other words, here all of my bonds are in a circle, or a triangle, I guess I should say. And if I can kind of just snap one of these, then it comes undone, and I have a more linear molecule. It's not actually linear. It'd be tetrahedral and then trigonal planar because I've got sp3 and sp2 carbons. Turns out this form is more isomerized to become this one. So at 720 degrees Kelvin, we have a rate constant, and we have an initial amount, and I want to know how much I'll have after 235 minutes. So we can definitely do that. Now with nothing on the screen, though, so let's put it all. Now, a lot like many other problems in this class, the worst part of doing these problems is figuring out what formula to use and also being careful with the units. Can you see something in here that will immediately trip us up? We'll see what happens when we get to it. So let's write out the integrated rate law because we know this is first order because the problem said so. So natural log of whatever it is at time t equals minus kt plus natural log of whatever initially. That's right, minutes versus seconds. So notice that the rate constants units are per second, but I want 235 minutes. So I need to change one of those to match the other. Otherwise, this isn't going to work. All right. I want to know how much I have at time t, which is going to be 235 minutes. So I need to solve for this, right? So let's e both sides. So we'll go e to the, and then e to the whole thing. E and natural log cancel out. So I have a at time t equals e, which I'm going to write as this, minus kt plus natural log of however much I start with. Hold on, actually. There we go. Now, you can rewrite this if you really wanted to, because if I have exp of something plus something, that's the same as me writing this, right? E to the minus kt times e to natural log of how much this is. I gotta put this outside. And then these would cancel out, which would just be this. So that's actually a lot simpler. So we'll just do that. But if you wanted to just solve for this expression because you don't know the rules of logs and exponents, that's fine. If we have time today, we're going to get to an equation that looks a lot like this, and it's going to be useful. So this is just where that comes from. So how much should we start with? We started with 0.0445 moles per liter times e to the minus k. So what is our k? 3.36 times 10 to the minus 5 per second times 235 minutes. And obviously, I can't just do this because these units won't cancel out, right? So I got to do something like this. So now everything will cancel out. So I've got seconds and per second. All right, so let's do everything that's in the E. So e to the, I wish Windows Calculator had an e to the, but it doesn't. E to the, parentheses, 3.36 times 10 to the minus 5. And then, oh, I have a problem here. I need to undo here. So I got to do that. There we go. Because I need that negative in there for my E. Times 235 times 60. So that's my E to all of that. I get 0.62. And then I'm going to times that by 0.4, oops, 0.445. So after 235 minutes, my concentration would be 0.0277. So if you were looking at that when I was doing this calculation, I don't know if I can scroll this over. I can. My result, my E, was 0.62. What I'm basically getting from this, I'm going to underline this in green here. This function outputs a percentage, and that percentage is the amount of stuff that remains over time, which is kind of neat actually, because you can enter the rate constant and then any amount of time, and then do e to the minus that, and you'll know what percent remains. So at 235 minutes, 62.2% remained in our container. And so that's what we did. We just took our number times that percentage, and then we got that. So I personally think that's cool. Most people don't give a shit, but I like numbers, so, you know. All right, so that's an example problem that you might have to do on the exam. Or the quiz. You could see the quiz. It's already posted. It should be posted. If it's not, I'm in trouble. All right, let's talk about second order. Second order works exactly the same way. It's just that when you integrate a second order rate law like this, so here's our rate law. This is the differential rate law, k times a squared, whatever that is. If I integrate this, then I would get something that looks like this. dA over a squared equals minus k dt. And so this is basically the inverse power rule, right? So I'd have a to the negative 2. And so I can multiply by some fraction or whatever. The exponent would decrease by 1, etc., or something like that. Anyway, the point is that when you integrate, you get this. We're not going to do the calculus, because it would take me forever to remember how to do the power rule backwards. But the result that we get is we get this equation here. You'll notice that there's a difference between second order equations and the other orders, first and zero order. And that is that the slope of this line is actually a positive number. This makes it immediately obvious when you plot something without even having to look at the axes. If you're looking at a graph and the slope is positive, you're looking at a second order plot. The slope is still the rate constant, because our equation here still models y equals mx plus b. And so all of this information just checks out from that equation. So here's my slope. The y-intercept is whatever my initial amount was, computed as an inverse. All right, so let's do an example with this. I do an experiment for the decomposition of NO2. This isn't balanced, but that's okay. And I collect this data. If I plot the data, here's my graph. I said, here's my graph. There we go. Actually, here's all of my graphs. So let's look at all of these graphs together. So here's the zero order graph. I plotted not natural. I plotted NO2 versus time, and you can, I guess I plotted against Tim E. I don't know what that is. But you can see that it doesn't really conform to my line very well, and that my R squared is not great. Then we got first order, and this is a little better. I have natural log of NO2 versus time. A little better, 0.97. And then we have inverse NO2 versus time, and then like, oh, it's a perfect line, because of course it is. The textbook gave me this data. So based on all three of these graphs, the most linear one being the inverse versus time, I can get the slope, which is this number right here. This must be the rate constant. 2.551 times 10 to the minus 1. And then these units are whatever they are to make the equation true. So if I have an inverse molarity as my answer, then whatever k times t is must also equal inverse molarity. And so that means that the constant for K, or I'm sorry, the units for K have to be inverse molarity times inverse seconds. So that the seconds here can cancel out with those. So that these are the units of this part and this part, which I can add together to get this part. If you aren't sure about that, and like you're looking at that and you're like, "Huh, I don't understand the units," write out all the units for all the terms. Write out the units for A over here. Then what would 1 over A be? What would 1 over A not be? These two subtract from each other. They have the same unit, so you can combine them. Yada yada yada. So you should be able to see how that works when you write it out. Now, because using all of these problems, or I'm sorry, using all these formulas works exactly the same way, I don't have a second order example. We're going to just go straight to the zero order reaction. I'm going to write this in. And then I'm just going to draw a line through it because anything to the 0 power is just 1. And so the differential rate law for a zero order reaction is just, it's the rate constant. That's all that there is. If I integrate this with respect to A, which I have here, and then T, which would then move to that side, I will just get KT as my result over the range 0 to A, or 0 to time T. And the integrated result that I have is just this. This is very obviously a line. Y equals mx plus b. So if you plot your concentration versus time, and you get a line that eventually just crashes straight into the x-axis, your reaction is zero order. The slope is negative, so the rate constant, well, you'll have to flip the sign on it, and the y-intercept is just whatever you started with. And there's really not much to do there. All right, let's talk about half-life. Half-life is a common term that is used for... I'm trying to think of other things that we use this for, but really what's coming to my head is radioactive isotope or valve game. Although, not really so much anymore because it's been like, what, 20 years since the last Half-Life game? So, yeah. But the half-life of a reaction is basically how much time do you need to elapse before half of what you started with has decomposed or reacted or whatever. The reaction for a first-order equation involves a bunch of logs and stuff. And we get a really interesting result. We're going to show this. I'm going to just show this to you algebraically, how we get this number. Where's 0.693 come from for half-life? And the answer is, well, it just comes from math. So if I start here, like this, and what I'm going to do is I'm going to say the initial amount that I have, we're going to just call it, I'm going to call it 2x. And then the amount that I have at time t, I'm going to have half of that, which I'm going to call x. This way I don't have to deal with fractions. So I'm just going to remove these. And just replace them with that. And now what I'm going to do is I'm going to solve for t. So I'm going to subtract my logs from both sides. And what I can then do is, well, if I have logs like this, when you subtract a log minus another log, that's the same as just dividing the two things, isn't it? Well, I mean, if you don't know your log rules, then this might be a surprise to you. And then what we can do here is we can go, oh, look, these cancel out. And so I get natural log of a half equals minus kt, which I'm going to divide by negative k, minus k here. I can't find the button on my pen to erase here. I actually set this up the other day. And then the last thing that we can do is that if I put this negative up here, I can then flip the order of these two things and make it positive. And guess what natural log of 2 is? Let's just do that. Natural log 2. Oh, look, 0.693. So we've proven what the half-life is. So you could do this for every equation. I just do it for this one because a lot of people are like, where the heck did this number come from? Do I have to memorize it? No, you don't. Because 1, I give you the formulas. And 2, you could derive it this way if you know what the rules for logs are. So, on the exam formula sheet, I wrote it as 0.693 over k. But you will oftentimes see it as natural log 2. And that's where it comes from. So basically, all you have to do is just say, okay, what's my rate constant? And just throw it in the equation. And then do natural log of 2 divided by that rate constant. And that will tell you how long will elapse for a substance to decay by 50%. And this will work regardless of how much you start with. I already wrote the proof, so it's fine. So there is no initial concentration in the expression, so it doesn't matter how much you begin with. For the other rate laws, when we do a similar treatment for math, the amount that you have does matter. But for this one, it doesn't. So let's do this example here. Iodine decomposes with this rate constant. It does this much per second. What's the half-life of the reaction? And so we would say, okay, well, T1 half is natural log 2 over K. And K is 0.271 per second. Well, inverse seconds is going to give us something in seconds. And so this couldn't be easier to punch in the calculator. We just hope that we get this type of question, right? So every 2.56 seconds, half of the reaction occurs. So at 625 Kelvin, half of our I2 will decompose into 2 iodine atoms. We will break half the bonds in a sample every 2.5 seconds or so. All right. Here's another type of problem that we can do with half-life. Let's suppose that a first-order reaction has a half-life of 26.4 seconds. How long will it take for its concentration to fall to 1/8 of its value? So I'm going to let you try this. And there's 2 ways to do this problem. And I want you to play around with it and see what you can come up with. We'll go over the answer in just a bit. All right, one more minute, we'll go over the answer. All right, so I'm going to show you the long way to do this problem, which is probably the intended way. And then I'm going to show you the easy way. And the easy way really only works for certain numbers. All right, so here is the half-life equation, which I can rearrange to get that, right? So natural log of 2 over 26.4 seconds. I can get the rate constant out of that. And so that would be, oh, it's natural log 2. I got to type that in first. Divided by 26.4. And we get that. Okay. Now if I go to the integrated rate law, for a first order reaction, I could say, well, if the initial amount is x, and the at time t would be 1/8 of x, we could just fill all this in, right? So this will be 1/8 x, and this will be x. And we can just solve for whatever t is, right? Because the x's are going to cancel out. I could also enter numbers in here if I really wanted to. But so natural log of 1/8 x minus natural log of x equals minus kt. And then, so we'll do natural log of 1/8 of times x over x. And the x's cancel out as long as x isn't 0. And then we'll just divide by negative k. So natural log of 1/8 over whatever our rate constant was. So let's take the inverse of this. So boop, there we did that. And then we're going to multiply that by 1/8. So there's 1/8. We're going to natural log that. We're going to times it by the previous number, and then we're going to negate it. All right. So that's probably the intended way to do this. Is you get the rate constant, and then you go back to the expression, and you solve the equation. Now, if you aren't comfortable doing this algebra, what you can do is instead of saying x, you can just put in any number. So, okay, maybe you started with 100, and then you ended with 1/8 of that. And then just do the numbers. It'll be fine. Here is the easier way to do this, and this works because we landed on 1/8. After a half-life has passed, so I'm going to start with this much. I will have that much, right? What happens if I have another half-life? Well, what I started with will lose half of that, right? What will happen if I allow another half-life to pass? Oh, look, I get the amount that I want in 3 half-lives. And guess what 3 times 26.4 equals? I bet it's that. Totally is. There you go. So that's the easier way to do this, but this only works if you land on a fraction that is a multiple of your half-life. So if you get something like 1/2, 1/4, 1/8, 1/16, 1/32, etc., you could just do it this way and say, oh, okay, well, that's 3 half-lives. So it's however long it took times 3. But for any other number, so if I ask you, like, what is it, how long does it take to fall to 44% of its initial value? That's not one of these fractions. So you'd have to do it this way, if that was the case. All right. So that's how we do half-life. That's for first order. For zero order and second order, the amounts that you start with do matter. So here's the second order half-life expression, which I'll let you try. What is the half-life of a second order reaction that starts with 0.1 molar and has a rate constant of 2.5 times 10 to the minus 2 per molar per second? So go ahead and try this. I'm not going to derive the expression because it's more or less the same thing that we just did. I am going to look something up, though. Hold on. Go ahead and work on this problem, but I do want to look up something because I feel like this formula might be wrong. Isn't there like a 2 in here? What am I thinking of as a 2? Oh, no, I'm thinking of the zero order equation. Never mind. Everything is fine. Go ahead and do the problem. One more minute, we'll go over the answer. All right, so same deal here as before. We're just going to use a different formula. We just set this up real quick. There we go. All right. So we've got our rate constant times however long or however much we started with, which would have been this. I don't know how to write numbers, sorry. So this and this cancel. This is the inverse on the bottom, so it becomes seconds. And so it's just all these numbers punched in. So we're going to go 2.5 times 10 to the minus 2 times 0.1. So this is what's on the bottom of the fraction. I'm going to just 1 divided by that. I got 400. Which is super inconvenient because I actually have to write it like this for sig figs. I'm certain I didn't do that on my slides. Yeah, I didn't. All right. Now the next question I have is, well, what if you had less than that? So if you had only half of this amount, now how long would the half-life be? So let's suppose I let a half-life go by. So 400 seconds pass, and now I have half of what I started with. What's the new half-life? I'll give you a minute to punch that in your calculator. All right, let's see what happens here. So now I am going to just, well, we're just going to do this. Something, obvious thing. Whoop. Was this faster or slower than me just writing the whole thing out again? I don't know. We'll never know. And so now we'll just do that again. So clear all. 2.5 times 10 to the minus 2 times 0.05 inverse. Uh-oh. Threw the pen on the table. And you'll notice that when the concentration is cut in half, the half-life doubles. Which makes sense, because if I put a number in this equation that is half as big, it's like multiplying by 2. All right, cool. I think we've done half-life enough. So 0 order, same thing. Here's our summary table. What information do I give you on the exam? So I'm going to highlight all the things that I give you. So I give you these equations, but I don't tell you what order they are. So you need to know which 1 is which order. And then I give you, let's see here. I gave you this, and this, and I give you this one. So that information I give you that's highlighted in yellow, I give it to you on the exam. I feel like the rate laws over here, stuff that I'm going to underline in red, I feel like you can create this, right? So, like, if something is first order, you're going to put a 1 up there. Well, you're not going to do that, but there we go. You're going to put a 1 here, and so on. So, I feel like that should be doable. All right. We're not going to do these problems because I don't have a graph, and we've done enough of them. Let's just talk about collision theory. We're sort of at the end point of, like, what's going to be on the exam, so everything past this point is just extra cool shit that I get to talk about. So, yeah, we'll do that after the break, because we're at a break point, I guess. So, sure, let's just do that. Let's see here. I'm going to hit play on... why is everything the worst? Hold on. Oh, it's over there. That's why. Okay. I'm trying to find stuff, and I can't. We'll come back in 10 minutes, and we'll see you after that. We'll talk a little bit about the rest of kinetics. I didn't mute myself, did I? Okay, cool. This is, like, my favorite Zelda wave track that's coming up, so I hope you enjoy it. All right. Welcome back. I hope everybody had a good break and you were able to pet a cat, fill your water. I forgot to fill my water. Oops. I focused entirely on the cat part. Anyway, we're going to just very briefly go over these next few sections just so we can round out the class. None of this is on exam number 2. There may be topics that show up on the final because the final is a standardized exam. Don't worry too much about that because I'm going to curve the exam based on what we have covered. Yeah, let's talk about some stuff here. So, okay. So, we have talked about how temperature is a mechanism by which we can manipulate how quickly a reaction goes or how slow it goes. If we want to slow something down, we throw a reaction in the refrigerator, for example. If we want to speed it up, we can heat it up. When you increase the temperature, molecules have more kinetic energy. So they will collide with each other not only more frequently because they're moving faster, but also with more energy. And so this tells us that, okay, if molecules bump into each other, and that's how reactions occur, Temperature must control how quickly the reaction goes. I'm not sure why this isn't advancing when I do that. And we have an equation for that, and that's called the Arrhenius equation. It looks like this. This equation relates the rate constant, K, which is what we've been working with, to temperature. But there's some weird stuff involved here. R, we already know. R is the ideal gas constant, which just shows up everywhere, right? E sub A is what's called the activation energy. So if you remember from energy diagrams, we have something that looks like this. The activation energy would be this hump right here. I meant to draw the line here, actually, but how tall that hump is depends on a variety of factors. Now, what about A? A is just a number that represents how often collisions occur and how often those individual collisions result in a reaction. So, we call it the frequency factor. And so, really, for our purposes, A is just going to be some number. We can solve for what A is by plotting the equation in the form y equals e to the x, where x is 1 over t. We're probably going to natural log this. Natural log k equals natural log a plus 1 over t times, yeah. Okay, so that's what we would have. Natural log k versus 1 over t should give us a straight line. And that's how we're going to solve for EA and also A. Oh, have we never seen this diagram? Maybe you haven't seen these diagrams. Maybe this is where I teach this to you. Okay, so this is an energy diagram. An energy diagram plots the energy of reactants versus products, and it draws a sort of path in terms of energy from being a reactant to being a product. And so another term that you'll hear for this is called reaction coordinate. For the longest time, I had no idea what this meant, and really all it means is how far along the reaction are you? So if you aren't very far along the reaction, then you're on the left side of this axis. You're at the reactant side. If you are far, you're at the product side. If you're in the middle, well, you're in an intermediary state. Everything has energy in it, right? So there's energy contained in like bonds, there's kinetic energy of the molecules, etc. All molecules have different energy, and that's tabulated in the thermodynamics tables in appendix like G or whatever it is. So we can estimate how much energy a collection of reactants has versus a collection of products based on like their delta H and their delta G and whatever. Now, in order to do a reaction, we need to have some minimum amount of energy to do that, for it to go. An example of this would be like if you had like a box of matchsticks. Matches don't burst into flames on their own. Otherwise, I would never be able to sleep at night. Thinking about my matches. Oh no, will my matches burst into flames tonight? No. In order for a match to ignite, you need to provide it with some energy, right? So what do you typically do is you strike it against some sort of like sandpaper or rough surface, or if you're like an old Western cowboy, you use the scruff of your cheek, or something like that, right? When you do that, you provide energy in the form of friction because it heats up the surface of the match to the point where the phosphorus and sulfur ignite with oxygen in the air, and you get fire. That energy that you have to input is the activation energy. Where does activation energy actually manifest? Well, if these two molecules, for example, this one right here and this one, if these encountered each other and they were going very slowly, what would happen is that their electron clouds around the nuclei of their atoms would encounter each other and they would repel. If the molecules are moving at very, very high speeds, though, the molecules will still repel, but they won't be able to repel each other enough to stop the molecules from colliding into each other, and all the electrons getting scattered in random directions. Basically, you can think of a reaction as like a car accident. Chunks go everywhere, the chunks in this case being electrons. And when the dust settles, you have a new arrangement of electrons. The orbitals are now overlapping, the electrons settle into them, the chaos arranges itself in an orderly fashion, I guess you would say. Now, unlike a car accident, when a reaction happens, you may or may not get useful products, so you may get something useful out of it. A car accident is just unfortunate. We don't want that. If you have the minimum enough energy to react, then you form products, and then the energy of those products is whatever it is. That energy might be higher or lower than the reactants, depending on the thermodynamics of what's going on. I have this as an example here. So this is a thing that can happen, believe it or not. Molecules that have bonds can do very interesting things that we wouldn't really consider to be normal. One of those is called a rearrangement. In organic chemistry, you're going to see this all the time, where atoms just seem to like hop from one place to another. They break a bond and form it somewhere else where that place is lower in energy. Here, for instance, the molecule on the left has a higher energy than the molecule on the right. The carbon-nitrogen bond, single bond, I should say, that right here, this is weaker than this carbon-carbon bond. And so what this molecule will do is if something were to like impact it, like say another molecule, or it hit the side of the container, like this sort of trajectory, then the CN part can spin like a top. And if there's enough energy to do that, it'll just go whoop and flip 180 degrees so that we now have the carbon in the middle and the nitrogen on the outside. The energy required to do this is the activation energy. And so if we put that on the molecule, or I'm sorry, if we put the activation energy on our energy diagram, we can see this. Now, in terms of the Arrhenius equation, where does the frequency factor come in? The frequency factor is going to be how often the molecule will like vibrate on its own such that it can actually rotate all the way, or how many collisions can occur at a given temperature that will result in this happening. It's a combination of those things. So here's our molecule initially right here. If it has enough energy due to like temperature or bonking into walls or other things hitting it or whatever, it can rotate. And if it rotates just enough to get halfway, then it will be right here on the reaction coordinate. At this point, the molecule has two choices. This nitrogen can pop back into place, or it can complete the revolution and the carbon can take its spot. Depending on what happens, it will either end up back as a reactant or as a product. If it turns into a product, this much energy is released. And that's the enthalpy of the reaction. The intermediate state is called the transition state. You may also hear activated complex, depending on which literature you're looking at. And then once you get to the final product, it will either remain that way, or if we hit it with enough energy to rotate it back to how it was, which would then require this much energy to do, it could turn back into a reactant. It does require more energy to do that because the products are lower in energy than the reactants. All right. Now, we talked about this a little bit before, but when we were talking about how we had concentration of our stuff times e to the negative whatever it was in our expression, we were doing the integrated rate law. We got a percentage for that, right? E to the minus anything is always going to be a percentage. Because if I have 0, which is the smallest negative number, we'll say, smallest absolute value negative number, we'll say, e to the 0 is just 1. So that would be 100% of things. If my activation energy for my molecule is 0, this becomes 0, and e to the 0 is 1. What that means is that if this is my activation energy, it looks like this. Oops, I didn't quite curve down there. If there's no activation energy, every single molecule has enough energy to react. But let's go the other way. What happens if I have an infinitely tall activation energy? If that's the case, e to the negative infinity is going to be 0. Because if I look at the graph of e to the x here, so e to the x looks something like this, right? This function approaches 0 at x equals negative infinity. And so what that means is that 0% of the molecules will have enough energy to overcome an infinitely tall activation energy. So we're going to have some value between 0 and 1 that follows an exponential function. A is just going to be some number that tells us how many collisions result in a reaction. And then this is going to just be a percentage multiplied by that. That will give us the rate constant. So the rate constant is really just this many collisions occur per second, per whatever the units are for molarity that are needed for the rate constant. And those units are going to appear in A also. It depends on the reaction order. Now, as temperature increases, right here, if I make T a bigger number, then negative E divided by RT is going to become a smaller number. And then when I negate that, that means that e to the negative that value gets closer and closer and closer to 1. If I did a reaction at t equals infinity, that would be some number divided by infinity, which would be 0, and then e to the 0 is 1. So at infinite temperature, the molecules have infinite energy and can overcome any barrier, except for one that is infinitely tall. So all these terms mathematically check out. All right, so here's our summary of the Arrhenius equation. You can bonk things into each other. The number of times that happens is the frequency factor. That tells us how many collisions there are that can react. The E term tells you what fraction of molecules can overcome the energy barrier. That fraction increases when you increase the temperature or as you lower the activation energy. And that fraction gets smaller if you do the reaction at a lower temperature or have a higher activation energy. We're not going to actually use the Arrhenius equation in this class, as far as I'm concerned. What we can do is we could plot it, like I said before. Natural log of k versus 1 over t will give you a line. You get a plot that looks like this. And so what this will tell me is that, okay, well, if I'm plotting this equation, this is the slope, the activation energy divided by the gas constant. And so if I was doing a reaction and I wanted to figure out what the activation energy was, I would just look at the slope. And I know that that slope, so negative 11,201 would equal minus EA over R. So I could just multiply this number by R, and that'd give my activation energy in joules per mole. And then I could also figure out the frequency factor here by just saying, well, natural log of the frequency factor equals that number. So therefore, A must be some ginormous number, because it would be e to that 26.79. All right. There's a shorter version equation of this where if you just have two data points, you can compare rates directly. That's nice and all, whatever, who cares? All right, let's talk about the collisions themselves, though. So if I want to look at the frequency factor A, I can rewrite A as this. And what we're going to do is we're going to define P and Z as two terms that will let us conceptualize A little bit better. We're going to call P the orientation factor. P is the percentage of molecules that are oriented in the correct way to cause a reaction. We're going to show a picture of that in a second. Z is just a raw number of how many molecules collide with each other. So if I multiply the total number of collisions by a percentage of the number of collisions that actually react, I get the frequency factor. Now, what is this orientation factor? I'm going to look at this reaction here, and I'm going to draw a picture of it. If Cl is the green marble on the board here, and NOCl is this thing right here, where N is blue, O is red, and Cl is green, would this collision lead to the formation of Cl2? Well, if this molecule bonks right into this guy, the opportunity for Cl2 to form exists. But what about this one? So if this molecule bonks into right here, can I make Cl2? Well, this is what these are going to look like. Here's my collision. Yay, that works. But what about this one? No, these would just bonk into each other and then repel, right? So what is meant by the orientation factor is that only certain collisions will work. If I'm looking at my molecule here, any collision in this region would work, but anything on this side of the molecule would not. Since that chlorine looks like it's taking up roughly a third of the molecule, I would predict that the frequency of collisions is roughly 1 in 3. So in this case, P would be like 0.33. Now, remember, this is happening in 3 dimensions. Because Cl is an individual atom, it's much more likely to be able to collide in an effective way than, say, two molecules bonking into each other. For instance, if I react these two molecules together, they have to line up in a very specific way, and the orientation factor is equal to 1.7 times 10 to the minus 6. Which means that in a million collisions, 2 will react. That's not very many. Fortunately, we have quintillions of collisions all the time. So this reaction will eventually happen, and if we're working industrial, maybe we want it to happen. Maybe we don't want ethylene, we want ethene instead. But for most purposes, a small orientation factor is not great. We may want molecules to react very quickly. And so if we can find a way to control this, such as like introducing a surface where I can stick the ethylene to and then the hydrogen can find it more effectively, that would be good. There are also very strange reactions. So for example, if I have potassium gas, reacting with bromine, you might think, oh, okay, my collision factor has to be between 0 and 1. Nope. For this one, per collision, there are 4.5 reactions. The molecules don't even collide. So, for some reason, with this molecule, what ends up happening is that potassium like throws its electrons at bromine as it passes by, and then it becomes ionic and more molecules collide into it. And they call this sort of like harpoon mechanism. It's very strange. So don't think that the number of collisions that can react, or the number of reactions that can occur per collision is limited to one. It can actually be any number it wants to, although higher than one is very, very strange. Most orientation factors are going to be less than one or much, much less than one. Now, as a thought experiment, I'm actually going to have you do this because I need to get more water so my throat doesn't get dry. I want you to tell me which of these reactions do you think has the largest orientation factor and which one has the smallest orientation factor. I'm going to number the reactions 1, 2, and 3. And I didn't mean to do that, so I'll go get my water. I'll be back in like 2 minutes, and then we'll talk about it. Alright, I'm back. Sorry, there were cats that needed to be hugged. And by cats, I really just mean Maya. I don't know if you have a cat, but the thing that I do with my cat is when there are the cats in the hallway, I don't try and walk past her, I just try and negotiate. Like, will you let me by? Meow. I need to go get my water. Meow. And we do that for like a minute, and then I eventually just pick her up and give her a hug. Alright, I'm going to draw this first reaction here. So I got H, and it's going to collide with I. And this is my goal, is to make HI. Hi. Hello. Now, you could probably guess that, well, any collision around anywhere would be okay, right? So the orientation factor would probably be close to 1. And that's because this reaction is spherical, or I'm sorry, these atoms are spherical, and any collision would be okay. But let's look at collision 2. So I have H2, and I have I2. What if I do this? If I do this, then an HI bond could form along this axis, but the other H and the other I don't have any way to meet each other, so this would not work. Instead, what we would need for this would be something like that, where now I would have this circumstance going on. And then each side could just go in this direction. So this would work. In other words, if I had a collision like on this side or on this side, that would be fine. But I would also need these to line up. So P is going to be pretty small. The smallest, though, is going to be this next one, because in order for this to work out, I can't do it this way. So not only do I have to have this like linear arrangement where I have everything line up in an orientation like this way works, but if I reverse them, I just get HI again, right? So these would pair and then these would pair, and that's not what I want. I would need to have them in this orientation so that I would get H2 and I2 again. So this P would be smaller, and in fact, I would predict it to be whatever this number is, divide by 2. Because half the molecules would be flipped around the wrong way. I have to have a very specific orientation for them to line up so that the reaction can occur. All right. That's really all I want to talk about for how reactions occur. We're not going to calculate the Arrhenius equation or anything like that. That's something that you can do in third-year chemistry if you really wanted to. I only have about 15 minutes left, so I'm going to talk about catalysts first before I talk about Oh, I just noticed that this isn't correct, but that's okay. I'm going to talk about catalysts first because I think catalysis is more important. If you're a biologist or a biochemical engineer, somebody that works with, I don't know, some sort of organism, catalysis is important for life. And the reason for this is because a catalyst is a substance that speeds up how quickly a reaction goes. But the catalyst itself is not used in the reaction, otherwise it'd be a reactant. So we want to at least know what a catalyst is, and see if we can get some examples here. Now, what this means is that if the catalyst is involved, then you're going to have a different sort of mechanism. We'll go back and talk about mechanisms fairly quickly so you get a general idea of what's going on. But a catalyst will change up what is going on during the reaction. So if A reacts with B, then you might have collisions between A and B, and then that's very slow. Like the orientation factor is really tiny. But by introducing a catalyst, maybe A sticks to the catalyst, and then B sticks to the catalyst, and then they're attracted to each other and form a reaction, and then they pop off. So the catalyst will change the nature of what's going on, but the end result is that if it's a catalyst, you always get the catalyst back. It can be used repeatedly. The activation energy is lowered in the presence of a catalyst, and so the rate constant goes up. That's basically it for a catalyst. So there are different types of catalysts. The first type of catalysis is a homogeneous catalysis, where if everything is, like, say, dissolved in water, then so will your catalyst. For example, if I have hydrogen peroxide, it will decompose in water. But if I add sodium iodide, it will rapidly decompose. Have we already seen this video? Surely we've seen this. Hold on. We did elephant toothpaste, right? Yes, we did. Okay, so we don't need to see that video. I was going to say, if we haven't done elephant toothpaste, we have to do that. But what's going on here is that instead of using iodide, we're using bromide here. The reaction is basically the same thing. In the presence of bromide, peroxide will react with it, and I will get an interesting intermediate that is unique to this reaction. That will then react to give me my catalyst back. So for this reaction, it looks like Br minus is being oxidized to Br2. And then peroxide is reducing Br2 back to Br minus to produce water and oxygen. What's important here is that the activation energy for this reaction, which would have been this versus this, you can see that it's much lower for that first step. And then for our intermediary step, this is its activation energy. And those are both smaller than the uncatalyzed reaction, so the reaction goes more quickly. Now, homogeneous catalysis basically just requires you to find the correct thing that reacts with your substance, and then you mix it in and hope that they collide. And they will, because there's tons and tons of molecules in your solution. But a heterogeneous catalyst... I gotta drink more water, sorry, give me a second. A heterogeneous catalyst can be more efficient. Typically speaking, heterogeneous catalysis involves surfaces. You're going to have your reaction that's in some phase. Sorry, I had to cough there. You're going to have your reaction, which is some phase, and then you're going to have your catalyst, which is in some other phase. A good example of this would be your car. When your car generates exhaust gases from the engine by combusting fuel and oxygen, you get a lot of waste products. So some of those waste products would be things like carbon monoxide. But because you're using air, and air is not pure oxygen, you're also getting nitrogen oxides as byproducts that we don't want. Nitrogen, NO, for example, is smog. NO2 is smog. Ozone is part of smog. And the purpose of your catalytic converter is for all of those gases that your exhaust has in them hit the catalytic converter and then decompose back into things like N2, which is inert, CO2, which is not inert, but is less harmful to the environment than, say, CO is, and so on and so forth. And the mechanism by which those things happen is that the molecules will stick onto the surface of the catalyst, and then they kind of just hang out until another molecule hits them that can cause the reaction to occur. Now, this isn't perfect, obviously, but it's way faster of a reaction than letting this happen just in the atmosphere, because the atmosphere is a really big place, right? And for the reaction to occur quickly in the atmosphere, we'd have to fill it with things like NO and CO, and we breathe that stuff, so that would be no good. Here's a visual of what's happening. This is a different reaction. This is ethylene with hydrogen. This is the reaction that we talked about earlier that had two reactions per million collisions. And basically what happens is that our ethylene gets stuck to the surface. It goes boop. And then the hydrogen also gets stuck to the surface. And what ends up happening is it then skitters over the surface until it finds the molecule and then can react with it. Now, skittering over a surface is still kind of random. As you can see, the path these atoms are taking is essentially random. But we're only worrying about 2 dimensions as opposed to 3. And if there are other ethylene molecules there, the hydrogen will find something to react with. In any case, the reaction occurs much, much, much more quickly on a platinum surface than it would just colliding in, say, the gas phase. In biology, you're going to have biological catalysts, and these are called enzymes. They follow what is known as the lock and key model. And that basically looks like this. You have an enzyme that will only fit certain shapes. And that certain shaped molecules will go into them. Those are called substrates. And what the enzyme does is it induces a chemical reaction that turns the substrate into products if the substrate is in the active site. Now, on its own, the substrate could do this reaction, but it's incredibly slow. So we use the enzyme as a catalyst to speed this up. For example, the decomposition of ethanol in your body is very, very, very slow. And ethanol is not super great for you, right? If you drink ethanol, you get drunk. In reality, being drunk is actually what we would call in either the medical profession or Dungeons and Dragons the poisoned condition. Yes, if you're drinking alcohol, you are poisoning yourself. And the reason for that is because you're introducing a chemical that does bad things to your biology. If we did not have the correct enzyme to break down the ethanol and oxidize it into acetaldehyde and then other things that we could then remove from the body through the liver and then the kidneys, you would basically be poisoned forever until it ran its course. And that would be terrible. Can you imagine if like you had one shot of whiskey and then you were drunk for like the next 7 days? Happy birthday, right? Like, no, that's terrible. Nobody wants to be drunk that long. It's only fun for a few hours. Drink responsibly. Trust me, when you get older, it's not great. So, catalysis is very important for biological reactions. I'm using the obvious one of drunk because virtually every student who's taking this class will probably experience that or has experienced like that in other people, or we all know what that means. But if I say something like some sort of enzyme or whatever that I'm not a biologist, so I don't know. I can't think of a good example, I guess. So there's our summary there. Catalyst will increase the rate of how fast a reaction will go by changing the mechanism. It's hard to predict the mechanism that involves a catalyst without doing various studies to figure out what is going on. But it's very common that if you do a reaction and a catalyst is involved, the order of the reaction completely changes. So you might have a first order reaction that becomes zero order in the presence of a catalyst. That is common enough. All right. We're going to skip my practice problem. This is literally a problem that was from my exam when I was a student, and I remembered this. You can read that if you'd like, but let's talk about mechanisms really quickly in the last 13 minutes of the class. And really, there's only one thing I want to talk about for mechanisms, and that is how do I figure out the rate law from a reaction? And the answer is we make a mechanism. A mechanism is a stepwise reaction blueprint. This is the important word right here. Stepwise. We are going to do reactions as simple as possible. Now, when I say simple as possible, what I mean is that if I have a reaction that does this, do you think that my reaction is going to involve all 5 of these entities coming together at once? And hopefully when you're thinking about this, you're thinking about what are the odds of 5 things crashing into each other all at once? I would hope that the thought that you're coming to mind is like, probably not, right? Have you ever seen a car accident where 3 cars hit each other all at once? I cannot think of one. Typically speaking, what happens is that 2 cars crash into each other, they create an obstruction, and then other cars hit that, right? So that would occur in a series of steps. There's the initial collision, and then there's later collisions. You don't have a reaction or a car accident where 3 things collide each other at the exact same time. That's incredibly unlikely. So with 5 entities, it's even more unlikely. So we're going to use that as our guideline. We're going to define an elementary step as the simplest possible step, and those steps are going to involve 1 molecule or 2, and that's it. You'll notice down there I'm omitting termolecular steps with 3 molecules because they are super, super rare. We're going to assume that three objects colliding all at once is essentially impossible. They do exist, but we're going to assume that it doesn't for our purposes. So we're going to define a reaction in a series of these steps, and each step can either have a molecule bonking into a wall and decomposing or doing something, or a molecule bonking into another molecule and then doing something. And so that's going to look something like this. Here's my ozone. It's going to hit a wall, and one of the O's falls off. That will be my elementary step. So this would be a unimolecular step because only one molecule reacted. So, for instance, if I have this as my reaction, then here is how I could do this reaction. You might think 2 ozones bump into each other, but in reality, this is much more likely. So step 1, an ozone breaks apart. In step 2, a different ozone breaks apart. In step 3, the 2 O's bonk together. And so now I have 2O3 makes 3O2, and these got used up. Now, why is this more likely to occur than 2 ozones bumping into each other? And the answer is, well, ozone is a trigonal planar molecule. I would have to orient those in a very specific way to get all my O's to line up. Because it's the 2 O's that are at the end here. I need to combine these two somehow, right? So the orientation factor of that collision would be very difficult. Whereas any ozone just breaking apart to create this is much easier to just combine 2 O's together, right? So this would be this right here would be the example of a mechanism. How would I test to see if the mechanism was what I expected? Well, I would measure the reaction order of various things. Or I could put a sensor in and test for the chemical presence of O by itself. That'd be a good proof, right? But the purpose is that we're going to split things into a bunch of steps. We're going to figure out what the slowest step there is, and then we can measure that one. Now, in this case, right here, this O that I made, this is called an intermediate. Intermediates have to get used up in the middle of the reaction. So that's why I was like, okay, I can make an O, that's fine. Would you normally have just O flying around by itself? No, you'd have O2 or O3, yeah? But if it's an intermediate, what we're assuming is that it's only going to be around for a short while. It's going to react with something before the reaction is done. All the reactions that we have shown you in the entirety of 161 through 163 have been just like net reactions of like, this is the end result. And it's nice that in the last 10 minutes, I have pulled out the last block from the Jenga tower and it all comes collapsing down. And you get to peek behind the veil and see, yeah, nothing that we've learned is true. There's always this other weird shit going on. Isn't that great? We're going to cover more of that in 261, where we'll talk about mechanisms in more detail. But the point of a mechanism is that we're going to have these elementary steps, a lot of which won't make sense because they will be so elementary that we'll just get intermediates that are like, O can't be by itself, Cl can't be by itself. Why are these things happening? And the answer is you can literally do whatever you want. You can break any bond you want. You can have any atom by itself. You can have any number of protons or electrons. But if it's unstable, it's not going to last like that for long. In a mechanism, we can assume that it sticks around for long enough for us to use it for a reaction. So when you sum all your elementary steps together, you have to get the overall reaction that you're trying to predict. Then the second thing that you have to do is you have to actually verify the rate law experimentally, and then match it to your mechanism. And there are various ways to do that, and the slides talk about them. It talks about the rate determining step, but I'm not going to bother you with that in the last 5 minutes because I could spend the entire lecture talking about mechanisms. Mechanisms are really cool, and if you move on to organic chemistry, you're going to spend a lot of time doing mechanisms on paper where you push electrons around and show that this is the product and that. But you know what? We'll leave that for you to explore with either Steve or Samita or Maxie, or whoever your OChem instructor is. So I think that that's where we'll stop. So we'll just, let's see here. Yeah, we'll just go to the end here. Hooray! All right, there is a chapter 20. We're not doing it. Yay! That's it. It's over. If I had like the strong bad, it's over, I would put it on the screen for you, but I might be the only person that knows what that who strong bad is. So, all right, that's it. I don't have anything else to talk about. We're all done with Chem 163, and you're all done with general chemistry. So that's exciting and great. I do need to get my little sound file up here. I want to thank everybody for coming to the lecture, especially those of you who came to the live lectures this quarter. Thanks for not leaving me alone to talk to myself for 2 hours. I do enough of that anyway. That was a joke, and then I did not follow up with that. So, yeah, that's all I got. So let's see here. There's an exam on Friday. Your quiz for Chapter 17 should be posted on Canvas. It's due Friday as well, but you can turn it in online on Saturday if you want to. The Chapter 17 quiz is all extra credit. The intent is just for you to try it and do it, and then learn something from it so that you are able to do those problems on the exam when you see them on Friday. The exam will be in the lab room with the chairs, White Horse 343. Just go to the same hallway. I'll open the door. You come in. We'll take the exam. You get as long as you need to do it, though I realize that if you're in bio, whatever, you have cures that day because Ricky emailed me about it. So, yeah, that's all I got. So we'll hit this button, and that's the last you'll hear of me. So we'll see you at the exam on Friday. Let me know if you need anything in the Discord. Take care.